Wellbore storage. Okay, so the easiest way to explain wellbore storage is it's simply a variable rate condition. It's a variable rate condition controlled by what? Class? Nice, Tom. That was good. I got to close this box. So tell me about this variable rate condition. What's it caused by? I know that, but what's it caused by? Okay, so you have an equation for rate that's a function of the change in wellbore pressure and the change in surface pressure. And then there's a coefficient over here like that. Okay? Can everyone see what I've done? This is a very straightforward equation. It says that rate at the sand face minus rate at the surface times the formation volume factor is equal to 24, because that's how many hours there are in a day, multiplied by CS. CS has the units of barrels per PSI, and then we multiply it by pressure gradient, or sorry, a pressure derivative with respect to time. So that's PSI divided by hour. That's where the 24 comes in. Okay? So what would be the easiest way to get rid of part of this problem? Kill that, okay? Does everybody just see what I killed? I said that the change in surface pressure with respect to time is 0. Is that true? Not exactly. What does not exactly mean? It means no. But for the sake of saying that I need a condition, I need a mathematical condition to make this easier, can I assume that that the surface pressure is constant? Yeah, sorta. There's a whole nother study of this problem where the surface pressure is not constant. That's called Wellbore phase redistribution case. And in that case, they work this problem with the dPTF dt term as not being equal to 0. We will work through this problem in this lecture, assuming we will not assume that's 0, but we still need to recognize that at some point we have to simplify this equation. There are two possible cases for C sub S. One is a liquid-filled or fluid-filled wellbore, and in that case, C sub S is equal to the compressibility of the wellbore fluid multiplied by the wellbore volume. That's very easy to understand. That's like a tank of compressible fluid. The next is a rising liquid or rising or falling liquid level. Santiago, what would this be like? Could this be like a pumping well, a sucker rod pumping well? Okay. So the wellbore is not completely full of liquid, but that liquid rises and falls with time. This coefficient describes that behavior. The equation that is given here is analytical. It's derived. There's no assumptions. Or if there are any assumptions, I don't want to talk about them. What assumptions are there? Is this for a liquid? Yes, it is. And what we'll show later on is that we can take that relationship and we can derive early time pressure relationships. How can we do that, class? What is the sand face rate at time equals 0? What's the surface rate? The surface rate when you open the well is whatever it is. Let's say it's 100 barrels per day when you open the top of the well. If a well has wellbore storage, what is the bottom hole rate? What is the rate at the bottom of the well? Correct. So if you solve that differential equation for the assumption that QSF is equal to 0, you will derive this equation. Okay? And that tells you what? That tells you that at very early times, for cases with wellbore storage, the pressure behavior is linear. This is very helpful for us in well testing. It doesn't do us any good, but it's very helpful. It helps us to understand the start of the test because it's dominated by wellbore storage. I didn't mention this, but wellbore storage is a bad thing. Wellbore storage gets in our way. Wellbore storage causes us problems. But the one nice thing about wellbore storage is it's like a tax, a TAX. You may not want to pay that tax, but you understand it's there, and it's sort of a reference. We do not obtain any estimates of reservoir properties during wellbore storage domination. We do not understand the behavior of the reservoir in any way during wellbore storage domination. Wellbore storage domination is something we have to pay for, and that's where you see that at wellbore storage domination, the sand face rate is equal to 0, the surface pressure is constant, and these are the results we get. Okay? So the rest of this lecture talks about what? It talks about deriving this equation, this QSF minus Q times B equals 24CS times that difference in derivatives. And the reason we go through that is so that you'll understand this is a rigorous mass balance. This equation is a rigorous mass balance on the system. I'm going to keep repeating that. What does that mean? Is that good for us? Is that bad for us? Anyone? It's good because it's rigorous and we understand what that means. It's bad because we cannot make this go away. How can we make C sub S go to 0? It's a trick question, please somebody. How do we make C sub S go to 0? I'm going to have a cigarette until somebody tells me something, and no, I don't smoke. Okay, that's one way. That's the most practical way. We could also make the wellbore fluid have a compressibility of 0, which is impossible, of course. So how do we reduce the wellbore volume, Santiago? No, physically. Come on. Okay, but I want to test a well. How do I reduce the wellbore volume to a minimal value? Okay, you get a hug. There's an electronic packer that closes the well off downhole, and it reduces the volume available for storage. The gauge is obviously below that, right? Okay, very good. Is that expensive? Yes. Okay, now we'll talk a little bit about the Laplace domain identity. At the end of today's lecture, you will have derived this. This result comes about why? This result comes about because the early time data is dominated by wellbore storage, the late time is dominated by the PSD function. And fortunately, the mathematics work out to give us something that looks like this. This is one of the most simplistic forms in petroleum engineering, and it will cause you to pull all your hair out. This is why I suggested that you use a model for PSD and you represent that model by some sort of an approximation. Maybe make a constant or a linear function or quadratic function. Okay? That's what the third assignment was all about. But this particular formulation is a pain. This particular formulation does not want to cooperate with us mathematically. There is no simple way to resolve this. This is an identity. We live with it. U is the Laplace transform parameter. PSD is the constant rate solution. PWD is the wellbore storage solution. And CD is the dimensionless wellbore storage coefficient. This seems so easy. And yet, it's so hard. But we'll talk about that. Okay, so very quickly, I want to orient you and talk about this. We have two cases. I know I'm not a very good artist, okay? But we have two cases. The first case, sorry, I'm going to steal a box here. The first case is a physical well that has what? It's totally filled with a fluid, okay? That fluid has a constant compressibility and we have a fixed volume. When you start with 1, which is m dot n minus m, or mass in minus mass out is equal to the accumulation rate, and then I wrote out everything that we have there. The final form of that equation is that the rate in minus the rate out times the formation volume factor is equal to 24 because the time is in hours for pressure. And then the change in wellbore volume, and that's our respective relationship. Okay? So that's our relationship for how this is represented. Now when we come to the next one, we have to start with a different kind of an approach, but it's still a mass balance. In this case, I'm assuming that it's a sucker rod pumping well, and the way this is going to work is we start with a material balance, which is the change in fluid volume is equal to Pi minus P bar multiplied by the compressibility. Oh, sorry, I'm reading from the wrong one. My mistake. Sorry. This is case 1. Case 1 corresponds to the other side. And so all of this is used to derive the equation for that case. Okay, my apologies, sorry. So case 1, we start with exactly the same kind of relationship we would start with for the If you remember the material balance equation for a black oil, this is exactly the same type of formulation. Okay? And we work through by differentiating it, and we end up with the expression at the bottom. Now the difficulty here is you have to understand that we're assuming in this tank sort of a pseudo-steady state behavior. So the tank doesn't have a transient in it. The wellbore does not have a transient in it, which is okay, that's logical. So the change in average reservoir pressure is equal to the change in tubing pressure, and then we have to include the influx, which is a change in wellbore pressure. So if we were just looking at the tank itself, we would be referencing the tubing pressure, but we're looking at the tank plus an influx from the reservoir. So the change in average reservoir pressure is equal to the change in tubing pressure here, and then subtracting the influx, the change in pressure here from the influx, okay? And so when we finally finish, we have the equation that I was talking about earlier, which is this QSF minus Q times B, which is an equivalent mass rate, 24 for hours in a day, compressibility of the liquid, volume of the wellbore, and then the pressure drop from the formation coming into the wellbore, and then the pressure drop at the surface, the change in tubing pressure with respect to time. So that's where that relationship comes from. And then finally, when we define our wellbore storage coefficient, and in this case our wellbore storage coefficient is a very simple relationship. It's just the compressibility of the wellbore fluid multiplied by the wellbore volume. We have a very straightforward result given by equation 9. And equation 9 is going to turn out to be a general result. Equation 9 is the same as we talked about on the first page. It's QSF minus Q multiplied by the formation volume factor equals 24, again, hours per day. CS, which has the units of reservoir barrels per PSI, multiplied by the change or the derivative of bottom hole pressure minus the derivative of surface pressure. And again, we're going to assume that the derivative of surface pressure is equal to 0 or that surface pressure is constant. The next derivation starts with the assumption that the change in volume, we're over here now, so the change in volume in this case is totally dependent on what? On the delta Z, the position of the fluid level. So we work this into a derivative, we take the limit, and we have the derivative of with respect to time of the wellbore fluid volume, the volume of the wellbore is equal to the change in the height of the fluid column, which makes perfect sense. So that's the definition of that for the rising or falling liquid level. Okay, so the pressure profile is then given by the hydrostatic. The hydrostatic is the bottom hole pressure, which is equal to the surface pressure plus the column of fluid on top of it, and of course that column of fluid changes due to delta Z. So then we work out what delta Z is, and of course we have these GC over G things, sorry about that for you metric people, and then we work that out, and we finally have an expression that says a change in the wellbore volume, that's equation 14, with respect to time, is 144 number of square inches, 5.615, square inches per foot. 5.615 is cubic feet per barrel. Area of the wellbore in probably in square inches, and density in pounds mass per cubic foot. GC over G are there as placeholders, and then the derivative of the bottom hole pressure minus the derivative of surface pressure. We continue to manipulate this, and we turn around and we solve for the rates, which are given by the differential in volume, and we close by adding or defining the wellbore storage coefficient as 144 over 5.615, area of the wellbore divided by the density and the G over GC relationship. When we finish all that, we get equation 17, which is exactly the same as equation 9. So both of these are mass balances on the system. Both of them have exactly the same formulation. So our final rate formulation for all cases, this mass balance I've been yakking about, is here. And this is our starting point for everything we're going to do. Okay, so that's our master equation. Now I talk about how to make this dimensionless, which is really not all that interesting, but this is the key. So if you want to simplify this equation, you can assume a constant surface pressure. Obviously, you cannot assume anything about the bottom hole pressure in this case. How about this? Somebody suggested to me they wanted to work on a constant bottom hole pressure case. If you assume a constant bottom hole pressure case, what happens to this relationship? No, forget fluid levels. Just look at this equation. I agree with you, but forget the fluid level. Just look at this equation. What happens if I assume a constant bottom hole pressure and a constant surface pressure? So the sand face rate and the surface rate are identical. So that's the premise behind constant wellbore pressure testing, is that you will eliminate wellbore storage. In practice, is that the case? Why? Because you cannot hold the bottom hole pressure exactly constant. And if you cannot hold the bottom hole pressure exactly constant, you're going to have a rate difference between the sand face and the surface rates. So unless you can derive a tool which perfectly manages downhole pressure to be constant, then you probably don't want to do this. But somebody in this room right now, or somebody listening to my voice, there's a little bell going off in your head thinking, I will create a business around testing wells with a constant bottom hole pressure. Somebody's smiling right now because they're thinking about that, aren't they? What 2 words do I have for you? How'd you know? Those are exactly the 2 words. Why is it good luck? Who tried this before? Everybody. From the companies that were first involved in well testing, to Schlumberger, to Flow Patrol, to Halliburton reservoir testing, everybody has tried to have a constant bottom hole pressure testing service, or a constant bottom hole pressure testing capability. This is what I'm trying to tell you. The practical aspects of petroleum engineering will drive you insane. Okay, we'll stop there for this discussion, and I want to skip over, and I want to talk about going down to the equation at the bottom, let's see, 27 and 28, and what happens when we assume that the sand face rate is 0. When we assume that the sand face rate is 0 at very small times, then we solve the integral. Let me grab a box real quick, sorry. So I'm going to start here, and you'll notice that I assume a constant tubing pressure, so that tubing pressure term went away. QD, gentlemen and lady, is just the sand face rate divided by the reference rate, or surface rate, and so that would be it would be equal to 0 if the sand face rate was 0, and so when we do that, And you can see that's right here. So we're going to assume that this gives us this expansion, which is pretty good, because now we can solve for the pressure profile as a function of time. The only thing that controls this pressure profile as a function of time is what? Is QB over 24 CS. And all of that's a constant according to our assumptions. Alright, so then we solved that and we obtained the relationship that the pressure at very early times is here. And that pressure corresponds to this plot. Okay? So what that tells you is that very early times in a drawdown, the pressure will decline linearly from initial pressure. Somebody explain to me why this happens in a practical sense. Where's all the fluid coming from when you open the well, class? Exactly. And that's exactly what this is telling you. So the mirror image of that is when you shut in the well, what happens at the sand phase, class? Nothing. The well keeps producing. That's right. So it's refilling the wellbore. So the pressure increase you see at very early times is basically just refilling the wellbore. So what I need you to remember is both of these plots, either the straight line on the drawdown plot or the straight line on the buildup plot, what do they represent in terms of reservoir properties? Five, 4, 3, 2, 1. Exactly, nothing. They do not represent anything to do with the reservoir. Are you interested in calculating the volume of the wellbore? No, you already know it. You know how many pieces of pipe you put in the well. You know where your tubing is. You know what the volume of the wellbore is. So again, this is all just a tax we have to pay so that we can get to the reservoir solution. But maybe we become desensitized to trying to get to that reservoir solution, and we look at this and we say, well, we understand the very early time behavior, so this is good. That's true, this is good. But it doesn't do anything for us. It doesn't give us any reservoir properties. It doesn't help us at all. But it does tell us where we are, and I guess that's useful. Okay, the last bit in the derivation is talking about how to derive the Laplace domain form. And I'll just say quickly that we use the previous result. We use the convolution integral. And we take that convolution integral and we take its Laplace transform. And then we rearrange, and we have our identity, which is here. And then we take the Laplace transform of our wellbore storage condition, and that's here. And then we marry them together, and that's here. And then we solve for PWD in the simplest form, and our final result is here. Any questions or comments about this? Questions or comments? Yes, ma'am. Yes, ma'am. Sorry, say that again. No, we cannot get QD in practice. Okay, KJ? We cannot estimate QD in practice. We have to assume a model for QD. QD is the sand face rate. Okay, if you're asking me, have people tried to measure this? That's true, but they're not very accurate, maybe 15 to 20% error. So this is why we assume a model to represent that. And our model to represent QD is given here by equation 26. This is our master model for wellbore storage, class. If I didn't make that clear, I apologize. There's two conditions. We can either solve it with the derivative of PTD equal to 0 or not equal to 0. We choose to solve it with it equal to 0. When it's not equal to 0, that's the so-called phase redistribution problem. And you can look up, there's a variety of papers on that. It isn't any more difficult, guys. You can simply substitute equation 26 in the Laplace domain form and solve it with that. But then you have to know the relationship for PTD as a function of time. Sorry, Ms. Lee, I went off on a tangent. What was your question? Sorry, say that again. Say it again for me, please. Well, we have a model for QD. It's given by 26, and 26 has the result in it. It has PWD in it. It has the derivative of PWD with respect to TD. So the point is that QD requires PWD. No, PSD is the known constant rate solution. We have to have that. So we must know CD and we must know PSD. Now, looking at equation 25, Ms. Lee, what we really want to do is we really want to solve for PSD instead of for PWD. We would like to take data for PWD, we would like to know CD, and we would like to solve for PSD. That's called deconvolution. Deconvolution. Unfortunately, that does not work very well. It does not like error at all. And there will definitely be error in both PWD, which is measured, and error in CD. Do you understand, everybody? The master relationship for wellbore storage is given by equation 35. The unknown for us is PWD. We know CD and we know PSD. In our case, PSD is given below. It's the radial flow case. It could be a horizontal well. It could be a vertically fractured well. It could be a hippopotamus. But we know PSD. And we assume we know CD. Okay, so what I was trying to do, because when you substitute PSD given by equation 36 into equation 35, you get this unmanageable mess in equation 38. Equation 38 cannot be solved directly. It has to be solved by numerical methods. Now, there is an analytical solution to 38. It's given below. It's given as 39. But that's a Moulin inversion integral. It is an infinite sum, and it is not going to be pleasant to try to apply. Look at it. I mean, it's the ugliest thing you've ever seen. There's no practical use whatsoever for equation 39. Equation 38 is the key. It has to be solved numerically, by numerical inversion, I mean. So what I was proposing is that we cheat and we put some other formulation in equation 35 that represents mathematically PSD. It could be an approximation in the case of, you know, I said it could be a constant, or I said it could be linear, or I said it could be quadratic. And I wasn't much older than you when I derived all this. I was sitting in class and I thought, well, why don't we try this? It seemed crazy. I didn't think it would work at all. But it actually did work. Okay, not great, but okay. All right, so let me move towards that and we'll finish this lecture. And so we talked a little bit more about what this looks like in equation 39, 40, and 41. Unfortunately, this is a log approximation. This cannot be reduced either. You either go to equation 39 or you solve it numerically, either way. Okay, so let's look at the graphs of this function. So we have the correct solution. This is the master, if you want to call it that. This is the Stayfest algorithm inversion. And so that's the master. And then we have the so-called constant PSD case here. And then we have the linear PSD case here. And then we have the quadratic PSD case here. And the constant PSD case, you know, your intuition is telling you this should not have worked. But it did. The linear PSD case, you're probably saying, well, okay, I didn't really think the constant PSD case should work, but maybe okay. The linear PSD case worked pretty well. You can see the dashed line is the approximation and the solid line is the numerical solution. And then when I went to the quadratic PSD case, it gave an even better match, although there does appear to be a little bit of, it appears that it sort of moved the error around. Not just an early time effect now, but it's kind of all over. But does all this make sense? So we have the master curve in black on the left, upper left-hand corner. Then we have its first approximation, which is the worst approximation. We have the second approximation, which is a little bit better. And then we have the third approximation, which is better still. And all of this was to simply see, frankly, if I could write an equation for PWD where I could use it in practice. Unfortunately, the constant PSD case is not good enough. And you need to say, what do you mean, Tom? What I mean is this part, this error that's in here, it's fairly significant. Let me also remind everybody, I'm going to jump over to comments for a second and steal a comment box. Okay, so this is wellbore only over here. This is reservoir only out here. I wish this thing would auto size. Yep. Sorry? Yeah. No, it goes away. You're talking about the difference between PWD and PSD? PWD becomes it becomes PSD at large times. Yes, it becomes PSD. So what I need you to understand is the wellbore only part. If you were to develop an algorithm to calculate things, what would you get from the wellbore only part, class? Only wellbore information. What do you get from the reservoir only part? Only reservoir information. What do you get from wellbore plus reservoir? 5, 4, 3, 2, 1. Nothing. You get nothing from the wellbore plus reservoir part. Nothing. Nothing. That's if we could improve our analysis or improve our capabilities of interpreting data in that region, then we could estimate reservoir properties. But we're asking for something that's too much. We're asking for data to give us information that it can't give us. Okay? So when you start looking at well test and you take a pressure transient testing course, you're going to become very familiar with this kind of a plot or this kind of an orientation. And you need to remember that you cannot estimate anything here. Okay, is everybody ready? We're going to go to the next slide. Let's see how smart I am. So how many people have disappeared from campus and there's no longer anybody working? If I were king, I would propose that we have Thanksgiving every 6 weeks. It's a great break. Use it wisely. Don't waste it on your family. Work for me. I'll be working for you. You know, we don't have BP gas stations in the United States, but my family and I one year we didn't understand that there are no restaurants open on Christmas Day in New Zealand. We thought maybe the Chinese place or the Indian place. It was our first year here, so we ended up eating dinner at the BP gas station. So that's my idea of holidays. Okay, so now we look at the derivative, and here it's wellbore only, here it's wellbore plus reservoir, and here it's reservoir only. I hope that makes more sense to you. And then we look at the approximations. I don't know if you can see my mouse. I'll go copy a box real quick. But you can see we've got a bit of error between the calculated and the analytical here. And we've got a bit of error between the calculated and the analytical here. Not much. The linear PSD case is probably sufficient for applications if you wanted to try to use it. It's probably sufficient for applications. Now I'll tell you, I wrote this paper and I never have gone back and tried to use this explicitly as anything other than just an explanation in class of how to try to solve something. Yes, sir. No, the problem is all of you think that we're using PSD constant as a constant. We're not using PSD constant for anything other than deriving the equation. When you apply the equation, you put PSD into the algorithm. You don't assume it's constant. You put actually PSD into the algorithm. So I cheated. I assumed it was constant only for the purpose of getting out of the Laplace domain. There is no use of a constant PSD in the application. There is no use of a linear PSD in the application. There is no use of a quadratic PSD in the application. We use the actual PSDs in the application. In other words, to generate these curves, I actually used the correct PSD function. But to derive the formulation that's in the paper, I used the assumption that PSD was constant, or PSD was linear, or PSD was quadratic to get out of the Laplace domain. That was it. I cheated. Does that make sense to everybody? If it doesn't, then, maybe I can explain it by going through the paper with you guys on Monday or Tuesday. Do you want to do that? Yes, I'm volunteering for more work. Okay, well, we'll plan on doing that. On Monday or Tuesday, we'll go over that paper. So everyone read that paper and come prepared to discuss it. Turmpon, you got that? And I'm going to send out an email to that effect. So on Monday, we'll talk about SPE 21826. And then we'll talk about the other two problems if you want. Now, I'm going to rely on Turmpon more for problem 1 and for problem 2. But I'll handle problem 3. Everybody happy? Okay. Go home. I'm sorry it's cold and rainy, but it's hot and sunny here, so I'll think of you when I go step outside. All right. Turmpon, would you do me a favor and send me a note? I'll send you a note to check the videos, but it's probably going to be at least an hour. The internet's running kind of slow. Okay, everyone, have a good night. Thank you for your patience. Good night.